Question 1. About how fast can a small fish swim before experiencing turbulent flow about its body? Question 1 is about a fish swimming in a pond, and it says how fast can a small fish swim before it starts to experience a turbulent flow around it. And the first thing you're not told in this question is how big a small fish is, and that's partly a sort of matter of pond size and tank size. So if you've got a something like a fish ladder where you've got a great big fish in quite a confined space, you've got that's not a small fish. It's something that's much smaller than the dimensions of the vessel or the pond or the ocean that holds it. And the next thing is, this is a Reynolds number question, and Reynolds numbers questions feature things called characteristic lengths or obstacle lengths. And if you go Googling what is the characteristic length in a Reynolds number problem, it's actually not a clear-cut thing. They'll find things that say things like it's got to be representative of the effect of the problem, but there's nothing that tells you, oh, it's this length. Although I did find one thing that says, well, actually it's the size of that you're pushing into the fluid. So for a fish, that's going to be like a sort of head-on view of your fish. So it's going to have its fins down this way and a tail out there, and it's a happy fish because it's in a physics problem. So what's the dimension of this fish? And I'm going to ignore its fins and say that this is L. And actually the size of your answer will be proportional to this length value, and whatever you pick isn't wrong, but scale your answer accordingly. This fish will have a boundary layer that becomes turbulent when R equals 100,000. So the thing that we're working out, we can take that as a limit case, and we've got the equation for a Reynolds number. R equals the density of the fluid, this obstacle length of the fish, the velocity it's swimming at, which is what we're trying to find, and then you get the viscosity of the fluid that it's swimming in, which is usually given the symbol eta. So we've got a value for Reynolds number because we're interested in this limit case where it starts to become turbulent. We know the density of water. That's one of those kind of nice geek facts that you ought to be remembering. This L, well, we've had a discussion about that. We're going to make up a number. V is the velocity of the fish, what we're trying to find, and eta is the viscosity of water. So R equals 100,000, write down what you know, always a good thing, and that has no dimensions. Rho is 1,000 kilograms per cubic metre. L is, well, I think this is my pet goldfish, and so I'm going to say that this goldfish is 2 centimetres. So 2 times 10 to the minus 2 metres is the easy way to convert centimetres to metres. And I'm finally left with eta, and eta for water is 0.01 Pascal seconds. So I bung all that in. Now I'll rearrange it first. So R times eta divided by rho L that we've made up is equal to V, and you bung in the numbers. That is 10 to the power 5 times 0.001, 10 to the power minus 3. I could save myself from work here, but I'm failing to do so. Divided by 1,000 and times 2 times 10 to the minus 2. So that gets rid of some of them. I'm left with 10, that becomes there. That's 10 to the minus 3. So that's, we've got 10 on the top, 10 on the bottom, times 2 here, and I end up with my V is 5 meters per second. If you do this with a different L, your V will be, for a bigger L, a smaller V. It's inversely proportional by the time you've rearranged it, but the method's the same.